You know, every single mobile developer out there is chasing the exact same thing, that perfectly smooth, high-performance user experience. We all know that feeling, right? When an app just feels liquid, gliding under your thumb. Well, today, we're going to pull back the curtain on how a pretty unlikely tech stack is making that a reality on Android, turning that frustrating lag into an experience that just flows. Okay, so first things first, let's define the enemy. It's that subtle stutter when you're scrolling, that frozen screen, that little moment of unresponsiveness that just completely ruins an otherwise amazing app. We're talking about lag, of course, and really understanding what it is, that's the first step to beating it. And I absolutely love this quote because it just hits the nail on the head. Tuning an app's performance isn't some kind of dark art or magic. It's a science. It's all about stopping the guesswork and starting to use tools that give you precise, data-driven answers. Now, the most famous, or maybe infamous, result of lag is the dreaded ANR. That's the application not responding dialog. It's basically Android's way of throwing its hands up and telling the user, hey, this app is completely frozen. It's the ultimate, most visible sign that something has gone horribly wrong. So what's causing that freeze? Well, it all comes down to the main UI thread. Honestly, the best way to picture it is as a single-lane highway. Every single thing you do, every tap, every swipe, every cool animation has to travel down this one single lane. Now, what happens if a big, slow-moving truck, like a heavy database query or a network call, gets on that highway? Everything grinds to a halt. A massive traffic jam. The entire UI just freezes solid. And this image really captures the philosophy behind why we need a new approach. As developers, we should be spending our time innovating, building amazing new features, not constantly fighting the limitations of our tools. That frustration is what drives the search for a new tech stack, one that's designed from the ground up to prevent these traffic jams from ever happening. All right, let's get into the first big piece of this high-performance puzzle. It all starts at the foundation with a complete and total overhaul of the graphics engine, swapping out the legacy system for something way more modern and incredibly powerful. And that's where Skia comes in. Now, if that name sounds familiar, it should. This is the exact same open-source 2D graphics library that Google uses to power Flutter, Chrome, and even core parts of the Android operating system. So, by adopting Skia, apps are suddenly using the same foundational graphics tech as some of the best-performing apps on the planet. But, you know, no technology is a magic wand, and it's really important to be honest about the trade-offs. Skia gives you a rock-solid graphics foundation, and it's ridiculously fast at drawing shapes. But there are downsides. It adds about 25 megabytes to your app's package size, and this is the surprising part. It can actually be slower when it comes to rendering images. And this benchmark just visualizes that point perfectly. You can see the legacy graphics canvas just churning out way more images per second than Skia. In some cases, for just raw image rendering, Skia can be up to 4 times slower. So that begs the question, how do you get all the benefits of Skia without this major drawback? Well, this is where it gets really clever. See, Skia has a kind of secret weapon for performance on Android, and it's all about cutting out the middleman and talking directly to the device's hardware. That secret weapon is called Vulkan. Think of Vulkan as a modern graphics API that lets the app speak the language of the GPU directly. It gives apps direct control, which dramatically cuts down on CPU overhead, and that overhead is one of the biggest culprits behind visual stutter and lag. I mean, just look at this table. When you compare it to the older OpenGL standard, it's not even a contest. Vulkan wins everywhere. It's got lower overhead, it's designed for modern multi-core processors, it even uses less power. But the key takeaway, the really crucial point, is that all this leads to deterministic, high frame rate rendering. In plain English, consistently, reliably smooth animation. So at this point, we've got a super powerful graphics engine talking directly to the GPU. The final piece of this performance puzzle is to optimize the actual UI components themselves. And the results we're about to see, they're just staggering. And this is where a framework called Alcinoe enters the picture. Think of it as a whole library of UI components that were built from the ground up with one single goal in mind: pure, raw speed. It's designed specifically to get around all the bottlenecks you find in standard frameworks. So how slow is a standard component? Well, a typical FireMonkey control, which is pretty common, can take about 3 milliseconds just to paint itself onto the screen. Now, I know what you're thinking. 3 milliseconds? That sounds incredibly fast, right? Well, just wait. Now look at this. The paint time for an optimized Alcinoe control is just 0.1 milliseconds. So how on earth is that possible? It uses a really smart technique called double buffering. So instead of drawing live on the screen, it pre-draws the entire control to a hidden image in memory. Then, when it's ready, it just blasts that finished image to the screen all at once. It's like having a painting completely finished and ready to hang instead of painting it on the wall every single time someone looks at it. Just let that sink in for a second. That's a 30 times performance improvement. A task that could easily eat up a huge chunk of your precious 16 millisecond budget for 60 frames per second is now so fast it's basically free. This is how you get that truly liquid smooth scrolling. But world-class performance isn't just about being fast today. It's also about being ready for the big architectural shifts that are always just around the corner. You have to be future-proof. And the next huge shift is already on our doorstep. With Android 15, Google is changing the fundamental way memory is handled, moving from 4 kilobyte memory pages to 16 kilobyte pages. And here's the kicker. This is mandatory. If an app uses native code that isn't built for this, it simply will not run on new devices. Period. So, why is Google even doing this? Well, to put it simply, the old 4 KB pages are just really inefficient for modern phones that have tons and tons of RAM. Moving to 16 KB pages lets the system manage all that memory much more effectively, which reduces something called page faults and boosts overall system speed. The really good news here is that the modern toolchain that's part of this stack is already prepared for this shift. The latest Delphi 12.3 compiler has been updated specifically to make sure all the code it produces is correctly aligned for this new 16 KB architecture. It essentially future-proofs these apps right out of the box. Okay, let's bring this all home. We've looked at the graphics engine, the GPU backend, the optimized UI components, and the future-proof compiler. What does this whole stack look like when it's all working together? And this right here is the key takeaway from everything we've talked about. Achieving that truly fluid, buttery smooth performance, it's not about one single trick. It's about the synergy of an entire modernized technology stack with every single piece working together in perfect harmony, from the compiler at the bottom all the way up to the UI components at the top. Which leaves us with one last big thought-provoking question. For years and years, developers have argued about which programming language is the fastest. But maybe that's the wrong question. Perhaps the future of performance isn't really about the specific language you choose, but about your ability to architect and assemble the right stack for the job.